Thank you for coming to our poster presentation. I will present to you our work of the adaptation of graph convolutional neural networks and graph layer-wise relevance propagation to the Spektral library with application to gene expression data of colorectal cancer patients. At first, I will give a short introduction. Colorectal cancer is one of the most prevalent cancer types in the world, and there are already machine learning models to guide the decision-making process for professionals, but they raise ethical and legal questions in precision medicine applications because they lack explainability in general. And we can use gene expression data to develop personalized treatment options and also use them as features for classification tasks with graph convolutional neural networks. To explain decisions of classifications on graphs, the graph layer-wise relevance propagation was adapted from the layer-wise relevance propagation, and we can use it to generate patient-specific subnetworks. And in this work we adapted the existing GLRP and GCNN to the Spektral graph library and adapted the functions for the graph layer-wise relevance propagation with this library and applied and validated our implementation on a new composed gene expression dataset of colorectal cancer patients with different molecular interaction networks as prior knowledge. Now we will continue with the dataset and interaction networks. The dataset was obtained from a gene expression omnibus from NCBI and contains 737 colorectal cancer patients with 303 healthy and 434 cancerous samples. The networks were all obtained from the Network Data Exchange platform, and we used the Human Protein Reference Database, Protein-Protein Interaction Network, the String Database, PPI Network, and the Reactome Pathways. Here you can see our data and training pipeline. On the left hand side you can see the input data with the gene expression microarrays and the use graph networks. We put our gene expression microarrays through a pre-processing pipeline using the robust multi-array average algorithm on each microarray, then combine those microarrays into one large set and quantile normalize them. And at the fourth step, we use the CMS caller R package to predict the subtypes for each colorectal cancer patient. And then we combine the gene expression microarrays and the graph networks and load them into the Spektral data loader. The data loader then passes the data through the Spektral model. We use two Chebyshev convolutional layers followed by a flattened layer and two fully connected layer and one output layer. Then we pass the outputs back through the network through the graph layer-wise relevance propagation and calculate the relevance of each neuron, which we then can use to create patient-specific subnetworks for our results. As our results, we compared the performance and computation times, examined the most occurred genes to identify gene expressions for colorectal cancer by generating those subnetworks through the GLRP, and analyzed the resulting subnetworks and overlapping genes for both implementations. And as you can see on the right, our accuracy and F1 score with the Spektral implementation was on average higher than the original implementation, but the AUC score was comparable, which could be an effect due to the class imbalance of our dataset and might indicate overfitting. And you can see that our average computing time was greatly reduced through improvements from the Spektral data loading, a custom data pipeline and training loop, as well as low-level improvements through the TensorFlow 2 library. Now we compared the most relevant gene occurrences for each network, and we can see in the table the top most relevant gene occurrences for each implementation and network, and we can see that the overlap between both implementations is very high beside the string network, but we were able to uncover possible more distant biomarkers for colorectal cancer with the Spektral implementation in the string network because its size is much larger and therefore the overlap is not really shown in the topmost gene occurrences. Now we compared the generated patient-specific subnetworks with both implementations. On the left you can see the original implementation and on the right the Spektral implementation for two patients, one with no cancer and the other with cancer. And you can see beside the layout that the Spektral implementation was able to uncover more distant occurred genes, and we can see that the uncovered genes were mostly overlapping with the original implementation. This can be continued for the reactome network, which you can see here, and the string database network. And finally, we can say that we achieved a high similarity in our resulting subnetworks of the colorectal cancer dataset using our Spektral implementation compared to the original implementation. We were able to identify valid marker genes for colorectal cancer risk and progression, and we achieved a much less computation times, especially when using large molecular networks as prior knowledge, and we achieved comparable, if not better, predictive performance than the original implementation. Here you can see our references. And this concludes our poster presentation. Thank you for your attention.